Okay, so interesting thing I figured out today. The infinitesimal change is represented by dy, and the infinitesimal change in x is represented by dx. But this is basically how differentials work. Now, before this, I was actually confused between the idea of a differential and the idea of a limit. Okay, so today I'm going to explain that distinction and figure out what I've learned. Tell you all what I've learned. So dy dx is basically just the slope of the y equals to x squared graph. Right, it's 2x, and then you get this thing, and actually it's pretty cool, right? Because when you want to calculate the change, for, say, if you change x by 0.01 meters, and x is just the length, because y equals to x squared is just the area of a square, and we can just treat this like, okay, it's an area of a solar panel, and the solar panel has a marginal error of 0.01 meters, right? It's just a measurement error, marginal error, and the engineers want to calculate, okay, if we have this marginal error, how much is it going to change our area by? Do we need to reduce our marginal error by using more accurate instruments? Okay, so what you can do is you can actually bring dx over to the other side, and then take 0.01, which is the marginal error, multiply it by the rate of increase, which, say, like, okay, the solar panel, we wanted it to be 10 meters, we wanted it to be 100 meters squared in area. Okay, then we realized that we actually change it by 0.01, it's going to be plus minus 0.2 meters square larger or smaller. So that's like 100.2 meters square. Okay, so not too bad. And the dy dx, what the dy dx actually represents, it can be treated like a fraction. It basically just means that for that small change in x, you're going to receive a small change in y. And proportionally, how many times is that small change in x going to affect that small change in y? So in this case, we get 20 square meters per meter. So for every meter that you change the solar panel in terms of its length, you're going to get an increment of 20 square meters. So if I had a marginal error of 1 meter, then my solar panel is going to be 120 square meters or 80 square meters, plus minus, remember? All right, so beautiful, that's cleared up. That's what the differential means. Okay, then I get to another confusing point. All right, oh, okay, but then when we're taking limits, why is it that as dx approaches 0, I mean, you see this in textbooks, I don't need to draw this out for you. Why is it that as dx approaches 0, we do nothing about this dy dx over here? Why don't we make it approach 0? Oh, well, that's simple, because this dx you see and this dx are two completely different dx's. Right, this represents the limits of the x. You're basically finding the limits of the graph, and after you find the limits of the graph, then do we talk about the infinitesimal change, because right now you're just finding the rate of change by itself, right? It's a very general thing. But when you want to zoom in, then you start substituting for your dy dx values. Okay, and mathematicians say, oh, this isn't a fraction. It's basically just a linguistic distinction, nominal distinction. It is technically a fraction, but it's just like confusing, because it's about taking things to limits. It's not a fraction per se, because you have to do all these orders of operations. Yeah, but this dx and this dx are two different things. So that was something I was confused by. Hopefully I resolved it for you. Yeah, but I still find it pretty cool, right? For that infinitesimal change in dx, you receive an increment in the area 20 times of that for the graph y equals to x squared. Right, pretty cool stuff. Okay, I even drew this graph for you here. So I hope this video was helpful to you, and it's easier than just computing this value. Nowadays you have calculators, back then they didn't. So you can imagine they use this. Then you might be wondering at the same time, okay, but what is yeah, so dy dx actually means, just tells you the rate, how many times that y is going to change relative to a small change in x. And small here is relative because your dx could be like 10 meters, and then your change in y is going to be like 200 meters squared. And then you're going to end up having an area of 300 meters squared, which is why y equals to x squared is like an exponential increment. Yeah, so I hope I cleared that up for you guys. God bless.